Notice copyright. You have seen this before and this. In video physics 06, we considered these 6 formulae: 4, 7, 8, 12, 16, and 17. In video physics 07, we considered these 3, 6, 9, and 15, which means that so far we have considered 9 of these formulae. All of these 9 formulae make use of a format such that the subject is equal to the product of 2 or 3 variables. For example, in F is equal to MA, notice F is equal to M multiplied by A. And furthermore, in number 7, P is equal to MV. That is to say, P is equal to the product of M and V. In video physics 08, we will be looking at these 3 formulae. And in this case, the subject, the one thing on the left-hand side, is equal to the quotient of the other 2 variables. That is to say, rho is equal to M divided by V, or P is equal to E divided by T. And for those of you who may have forgotten, the quotient is the result obtained by dividing one quantity by another. So we begin by looking at formula 5. In this formula, rho is equal to M divided by V. And the Greek letter rho stands for density in kilograms per cubic meter. M stands for mass in kilograms, and V stands for volume in cubic meters. This formula has 3 variables, rho, M, and V. Given any 2, the third can be easily calculated. So let's look at example 1. A concrete block has a mass of 800.0 kilograms, that is 4 significant figures, and a volume of 0.12 cubic meter, that is 2 significant figures. What is its density? So you know your answer can only have 2 significant figures. So we write down what we are given: mass, volume, we want to find density. Just a reminder, this number here has 4 significant figures. This one has 2, and so our answer will have 2 significant figures. We have a formula that says rho is equal to M divided by V. We substitute the numbers we are given, the values we are given, and we get density is equal to 6,666.66667 kilograms per cubic meter. We know we cannot leave our answer like that, so we'd have to round off to 2 significant figures. 1, 2, because this is 5 or more, that becomes 7, and we add 2 zeros to keep the decimal places. And since we are rounding off at the hundredths position, we will take half of that position, which would be 50. So it would be plus or minus 50 kilogram per cubic meters. So our answer is 6,700 plus or minus 50 kilograms per cubic meter. Now, this is also correct, but CSEC prefers to have the plus or minus format, like we have here. So this is our answer. Example 2. A body has a density of 12,300 kilograms per cubic meter and a volume of 400.0 cubic centimeters. Calculate its mass. So we write down what we are given. We know the density. We know the volume. This is in cubic centimeters. Our formula, we have V in cubic meters. So we need to carry cubic centimeters to cubic meter. Just a reminder how that is done. 1 cubic meter is equal to 1 million cubic centimeters. So to carry cubic centimeters to cubic meter, we need to divide by 1 million. How did we get that? Think about a cube that has sides 1 meter, which is 100 centimeters, 1 meter, 1 meter. So the volume of this cube is 1 meter by 1 meter by 1 meter, which would give you 1 cubic meter. But if we calculate that in terms of centimeters, it will be 100 centimeters times 100 centimeters times 100 centimeters, which gives us 1,000,000 cubic centimeters. And that is how we know that 1 cubic meter is equal to 1,000,000 cubic centimeters. So we divide that 400.0 by 1,000,000 and we get this. This one has 3 significant figures. This has 4 significant figures. And so our answer will have 3 significant figures. We want to find M. We know that density is equal to mass over volume. We change that to make M the subject, and we get M is equal to rho times V. We substitute the numbers we are given, and we get 4.92 kilograms exactly. And that is sufficient for CXC. Remember, our answer requires 3 significant figures, and this is 3 significant figures. So that's our answer. Now you can write 4.92 plus or minus 0.005 kilogram, but you are not getting extra marks for that. 4.92 kilograms correct to 3 significant figures. That is also correct, but do not use this format for CSEC, as CSEC prefers a plus or minus if you have to write it. But in this case, we do not need to write it. 4.92 kilograms is fine. So we considered that one already. We are now looking at formula 13, which is P is equal to E or W over T. P stands for power, and it is measured in watts. E or W stands for energy or work, and that is measured in joules. T stands for time, and that is measured in seconds. Note that energy expended or work done is the same thing, and both use the same unit of measurement, the joule. So we have 3 variables given any 2. We should be able to easily calculate the third. So example 3, a man does 4,000 joules of work in 50 seconds. What was his power output? Notice that this is 1 significant figure. This is also 1 significant figure. So our answer can only have 1 significant figure. We write down the work, the time. We want to find the power. Power is equal to W over T. We substitute the numbers we are given because power is already the subject of the formula. And we divide 4,000 by 50, and we get 80 watts. This is already 1 significant figure. However, as I said, that may be subject to misinterpretation, and we'll get back to that. But note that if you divide joules by second, you get joules per second. Technically, that is correct. However, this derived unit, joules per second, has a special name, which is the watt. If you write joules per second, you will lose a mark because you did not write the right unit. Joules per second, the correct name for that is the watt. And while technically joules per second is correct, you will still lose a mark for that. As it relates to significant figures, we are rounding off at the tens position where this 8 is. So we need to put in a plus or minus 5 watts. You can also say 80 watts correct to 1 significant figure. As I said, CXC recommends this format. If you find this video useful or interesting, please like and share. Like, share. You may also consider subscribing to this channel. We continue with Formula 13 with example 4. A machine does 50.0 kilojoules of work at an average power output of 200.0 watt. How long was the machine on? So we're given work, we're given power, and we want to find time. Note that this is 3 significant figures. This one here is 4 significant figures, all 4. Now our formula cannot take kilojoules, it has to take joules, so we need to convert 50.0 to joules. So we remove the K from there and put in 3 zeros, which is 1000. 200.0 watt, that's fine. We want to find time. We know that P is equal to W over T. We can rearrange this equation to make T the subject of the formula, and we get T is equal to W over P. We substitute the values we calculated, and we get exactly 250 seconds. But where is our uncertain digit? Is it at the ones or is it here? Now, since we want 3 significant figures, we will have to round off at this ones position where that 0 is. And so our answer is 250 plus or minus half of the ones position, which is 0.5 second. 250 seconds, correct to 3 significant figures, is also a correct way of writing it, but CXC prefers the plus or minus format. Of course, you can also write it as standard form, which is 2.50 times 10 squared second. Notice the 3 significant figures there. This is the format here, this plus or minus, that CXC recommends, or rather that CXC requires. Now we turn to Formula 14. P is equal to F over A. Now that P up there in Formula 13 was power. This P here in Formula 14 is pressure, and it stands for pressure in measured in Pascals. F stands for force or weight measured in newtons, and A stands for area measured in square meters. Now this formula, this one that we see here, is used to measure pressure when a solid object rests on another solid object. Example, a water tank resting on a concrete slab. Now recall previously from Formula 15 that delta P is equal to rho G delta H, which is used to find pressure on a body submerged in a fluid. So we have 2 formulae for pressure, the one we are going to look at right now, and the one we already looked at in Formula 15. Now this formula here, P is equal to F over A, has 3 variables. If any 2 are known, the third can be easily calculated. So example 5, a filled water tank has a weight of 80,000 newtons and a surface area of its base in contact with the concrete slab it rests on is 2 square meters. What pressure in kilopascal does it exert on the concrete slab? So we write the data we are given. F is equal to 80,000 newtons, which is the weight or the force. Area is equal to 2 square meters, and we want to find pressure. Notice that this 80,000 has 1 significant figure. This 2 square meters here has 1 significant figure. So our answer can only have 1 significant figure. Okay, we have a formula that says P is equal to F over A. We know the values of F and A. We substitute those and we get 40,000 pascals. But we want our answer in kilopascals. So we take out the 1000 and put in K, which is the same thing. 40 K Pascal is 40,000 pascals. So 40 kilopascals, but we're not yet finished. Since we are rounding off at the position here where that 4 is, which is the tens position, we will take half of that tens position and we get 5. So our answer is 40 plus or minus 5 kilopascals. As I said, that is also correct, but CXC requires this format. Now, you can set it to standard form, then it becomes 4 times 10 to the first power kilopascal. Note, 80,000 newtons divided by 2 square meter is equal to 40,000 newton per square meter. That is technically correct. But this derived unit, newton per square meter, has a special name, and it is the Pascal. By the way, what you have here is a definition for the Pascal. The Pascal is the force of 1 Newton acting normally, meaning at right angles, on an area of 1 square meter. We now look at example 6. A lady of mass 61 kilogram presses on the wooden floor temporarily when she rests all her weight on one steel-tipped stiletto-heeled high heel shoes, and the heel itself measures 4.0 millimeter by 6.0 millimeters. How much pressure does she exert on the floor at this time? Assume G is equal to 9.81 meters per second squared. Notice that is two significant figure. This is two significant figure. That is two significant figure. This is three significant figure. So our answer can only have two significant figures. So her mass is 61 kilograms. We need to carry that to newtons by multiplying by G, since weight is equal to mg. So we get 598 newtons. The area of the shoes, the heel, is 0.004 meter multiplied by 0.006 meter, and so we get 2.4 exponent negative 5 square meters. So what we did is that we convert the millimeter to meter first. 4.0 millimeter we divide by 1,000 and we get this meters, and we do the same thing for the 6 millimeters. So we get an area of 2.4 exponent 10 to the negative 5 square meter. We want to find the pressure that she exerts on the floor. Well, we know pressure is equal to force over area. We substitute the values we calculated, and we get 24,916,666 pascals. We cannot leave it like that. Two things we are doing here. First of all, we are going to round off to two significant figures. And if we do that, then all of that is gone with a 5 here and a set of zeros behind it. As a matter of fact, 6 zeros. 1, 2, 3, 4, 5, 6. So now we have 25 million pascals, but we can remove all of those zeros and put an M for megapascals. So we have 25 megapascals, and since we are rounding off at this position where the ones is, that would be half of that plus or minus, so we get 25 plus or minus 0.5 megapascals. Or you could have written it in scientific notation, 2.5 times 10 to the 7 pascals. Do not confuse pressure with force, which sometimes happens. Recall from the previous water tank example, the pressure was 40 kilopascals. This means that this 61 kilogram average size lady exerts 625 times more pressure on the wooden floor than the water tank on the concrete slab. Enough pressure to dent the floor or badly damage someone, in self-defense maybe, if she presses down with all her weight on her attackers instead. like this. So this is the attacker's instep, and this is the high heel shoes. That high heel there will exert a pressure of 2.5 times 10 to the 7 Pascal, or 25 million Pascals on the attacker's instep. So these 9 formulae were done before. We just did these 3. At this time, we have 9 of these formulae covered, those that are in white, which means that we have those 5 more in yellow yet to do. If you have learned this so far, you are making much progress. 5 more to go in mechanics. And that brings us to the end of this video 8.